we're starting Unit 7. And if you look on the wall, if you look at that scope and sequence, which I also have in the unit folder in Blackboard, if you look at the scope and sequence of calculus, it's like the second to the last unit for AB. If you notice, it's short. There's not much there in terms of daily content. So it's like a unit 3 or a unit 4. And it's very specific. So we're talking about one thing and one thing only, and that's something called differential equations. There's a couple of topics in there that are purple. That's for BC, so you can ignore those topics. So this is like I said, it's a short unit. And so on the board here is our schedule for the unit. Our first quiz is coming up in a couple of days. Okay, so the takeaway from the notes, as we are looking at these notes, differential equations are derivatives. You've been dealing with them all year long. Okay, so you might think, well, why the fancy term? We'll get into that. Okay, but they represent derivative values for a family of functions. So for instance, dy dx equals 3x squared. That's a differential equation. It's got an independent variable, it's got a dependent variable, it's got a derivative. It represents a derivative of what? Okay. How about, can you think of anything specific? Like what function do you have to start with in order to get that as a derivative? X cubed, right? Or y equals x cubed, right? Is that the only function that leads to a derivative of 3x squared? Okay. Right? How about y equals x cubed plus 4? Does that make sense? We differentiate that, the 4 goes away because it's a constant. What's the difference between those two functions? This one and that one. Yeah. Yeah, there's a plus 4. What does that do to the graph? Right? Just shifts it up. But all the tangent lines, would they look the same at a particular point? Would they have the same slope? Yeah, right? Everything looks like that classic x cubed. Remember, I have all of those functions on the back of your schedule on the front in your packet, and x cubed is that classic S-like shape. It's just up 4. So all our tangent lines have the same slope at the same locations. Or how about x cubed minus pi? Right? Pi is just a constant. So just like you said a moment ago, I've forgotten who said it already now, but it represents that general family of functions of x cubed plus c. Okay? Where that c is a numeric constant, differentiate it, it's 0. So you get 3x squared. And this is what we refer to as a family of functions. With a family of cubic functions that all differentiate back to this differential equation. Because that differential equation describes slope values everywhere along that function. Any of those functions. Does that make sense? Okay. So differential expressions are a function of the same variable, right? The differential expression here is a function of x, and its parent function is written in terms of the variable x. We have direct and inverse relationships that we're going to be focusing on. Direct relationships look like this: dy dx equals k times x, kind of like this. Right? This is k times x squared. It's a numeric constant times a function. A specific a family of functions. Or we have an inverse relationship, k over x. where we're, instead of multiplying by a function, we're dividing by a function. So if we talk about this being a derivative, we know that the solution to this, the antiderivative, is something like in terms of x squared. In other words, the original function is some sort of function of x squared, or some sort of polynomial type looking function. If we look at the antiderivative here, or the solution to, notice I'm kind of blending words here, antiderivative, solution to the function, those are one and the same. If we look at the antiderivative here, that is the family of natural log functions. Okay, so we start to see these, and I call them families because of this constant of integration that can be differentiated out. So we kind of are breaking our differential equations into two big barrels, so to speak. We're going to look at things that end up being polynomial. We're going to look at things that end up being natural log or logarithmic in general terms. So far, so good. Okay, so solutions to differential equations are those expressions that can make the statement algebraically true. So sometimes there's a family of solutions. Sometimes there's one particular solution. And we'll get into when those occur and what that looks like as we go through the unit. So any questions there? Okay, so really our focus for today is, what are differential equations? They're an equation involving x and y prime, or dy dx. They're a derivative. They're a representative of a family of functions. So any one of those descriptions. Okay, when we talk about involving x and y prime, we're talking about independent and dependent and derivative sort of vocabulary in reference to those notations. All right, so we've got some topic questions, and then we've got some homework. I think it's one or two. Oh, it's right there. No, it's two cons. We're back to con now. We're not doing this jumping around to different platforms anymore. You've made your voices heard. We're working on the decision. So we got topic questions. We've got day 2 notes. We've got 2 cons on tasks for tonight. So short unit. Please try to stay current. Don't get behind in your cons or anything like that. All right, go ahead and get started, and I'll be around to check in with you and see how you are doing.